Now, there's also something known as a stride. So it defines the interval at which you place the filter. So far in all the illustrations, what I was doing is, I was moving the filter 1 pixel at a time, right? So I placed it here, then placed it at the next pixel, and so on, horizontally and then vertically. But I could also place the filter at every alternate pixel, right? So I placed it on the first pixel, then on the third, then on the fifth, then on the seventh, and so on. So in that case, my stride would be 2. So this is how that would operate. Just notice how that blue block slides, okay? Do you see that I'm only sliding it to every alternate pixel? I'm not going on every pixel, but every alternate pixel. So in this case, if my original input is of size m, my output would be order m by 2. If my stride is of size 3, m by 3, right? So now, will you be okay if I give you the following formula? I basically divide it by the stride. Is that okay? Don't worry about this extra 1 here and there and all that. Whatever width I'll get, I'll just divide it by 2. Because I'm only placing it at every alternate. If the stride is 3, it will get divided by 3. If the stride is 4, it will get divided by 4. Everyone gets that? Okay? So now we are done with width and height. Now finally coming to the depth of the output. Now I had some n 3x3 filters. So I know what the W2 and H2 is going to be. Now what is the depth of the output going to be? If I have k filters, each filter will give me one 2D output. So what's the depth of the output going to be? K, right? So I have k such 2D outputs. So if I stack them together, I get one 3D output whose depth is equal to k. Is that okay? So the depth of the output is equal to the number of filters that you have. Is everyone fine with this? Yeah. So if I have one filter, I'll get one 2D output. And I gave you the exact formula for what the width and height of this output is going to be. But if I have k such filters, each filter is going to give me one 2D output, right? So I'll get k 2D outputs. That's the same as saying I have one 3D output whose depth is k. Does everyone get that? Everyone fine with this? Okay. So the depth is going to be equal to the number of filters. So now if you have understood this, let's do some exercises. So I have an input of size 227 cross 227 cross 3, and I've given you other details here, the number of filters, the stride, the padding, and also the formula. I want you to tell me the formula. I want you to tell me the dimensions of the output. What is W2, what is H2, what is D2? First tell me what is D2. Everyone, what is D2? 96, because D2 is equal to the number of filters. And I have 96 filters. Now what is W2 and H2? Sorry? 50. 54. Any other answer? 227 minus 11 plus 0 divided by 4, that is 54, plus 1, that is 55, right? And same for the height also. Everyone gets this? Everyone is fine with this? Okay. So you can compute this. Now I have another exercise, but you can do it offline. Okay. So now I started with neural networks in the previous 2 lectures. And then I took this detour and explained what a convolution operation is. Now what's the relation between a neural network and a convolution operation? I have not told you that, right? I mean, we started with sigmoid neurons and all sorts of neurons. We had this weighted aggregate and so on. And then we just moved to this convolution operation. And what's the connection between the two, right? So that's what we are going to do now. What is the connection between this operation, which is the convolution operation, and the neural network? I'm assuming all of you are completely comfortable with the convolution operation, including how to compute the dimensions of the output and all, right? So now we'll try to understand this, that how is all of this related to neural networks. We'll want to understand this, and we'll take the example of image classification, okay? So this is the task of image classification. You're given an image, and earlier, remember I told you I have a 30 cross 30 image, and I want to classify it into apples, oranges, and so on. And you said that you can just take the entire 30 cross 30 input as one input vector. That means your input was of size 900. And with this input, you want to produce one of 4 classes, okay? So the naivest way of doing image classification would be take the image, flatten it out as a simple vector. So you get one 900 dimensional vector. And then you apply anything, right? You can apply, what are some of the classification algorithms that you have learned here in this summer school? SVMs? Sorry? Okay, so any of these, right? Say SVMs. So you could take this 900 dimensional input and pass it through an SVM algorithm and learn how to predict the output, right? So that's the simplest thing that you could do. So that's the naivest way of doing image classification, right? But then you could do also something more smarter. You could do some handcrafted. So notice that I want to find the difference between 4 classes: car, bus, monument, and flower. And intuitively, it feels to me that all the details inside the monuments are not important. It's not important that all these are white pixels or orange pixels or green pixels. What I care about is the shape. If the shape has a lot of domes and pillars, then it's definitely not a car or a flower or a bus. If the shape has a lot of things like a bonnet and a dicky and some car wheels and so on, then it's probably a car, right? So what matters to me is the outline. So if I have to come up with this outline, what can I use? I could use that convolution filter which gave me the edges, right? So, but that's handcrafted. That's based on my knowledge of this problem. That here, because if I wanted to differentiate between different flowers, right, then the outline itself may not be sufficient. There might be some details in the petals or pixels which might be more important, right? 2 flowers in the outline might look similar, but the color of their petals or the configuration might tell you something different, right? But let's assume this problem, I could do some handcrafted feature engineering, and instead of using the raw pixels, I could use these transformed pixels, right? And then again train an SVM on top of that. Is that fine? Okay. But then people realize there's something more better than this. This is something known as sift and hog features, which were widely used in computer vision prior to 2012, 2011, that is prior to the deep learning boom. So these actually tell you something about how the pixel values change across the image, right? Very roughly speaking, it tells you something. So hog is known as histogram of gradients, so it tells you how the gradients change across the images. So this is again, if you look at the second image here, right? It's again trying to capture some abstract representation of the image, but this is again deterministic in the sense that you give it an input, you apply the sift or hog algorithm to it, and you'll get the transformed image. If you do this 100 times, every time you'll get the same transformed image. Is that fine? Okay. So we had this raw pixels, then we had handcrafted pixels or handcrafted features, and then we had a better way of coming up with these pixels, which was again handcrafted in some sense, because someone came up with this sift and hog algorithm and showed that this is a better way of representing the input image. So instead of using the raw pixels, use the sift or hog transformed pixels. Is that fine? Okay. And now once you have these features, you can apply again your favorite classification algorithm, which is SVM or anything else, and learn the parameters of that algorithm. So in this setup, in all of these 3 images, what are you learning? In all these 3 cases, what are you learning? You are learning the weights of the classifier, the final classifier. That's all you are learning. Is that fine? Everything else is given to the classifier in a deterministic way. If you want to give the pixels, that's just deterministic. Flatten out the image and give it to it. If you want to compute the sift hog features, just run that algorithm. You'll get some representation, give that to the algorithm, and based on that representation, it will learn the weights. Does that make sense? So the only learning happening here is in the last layer, which is the output layer, or which is the classification layer. Is that okay? Okay, so this is all static feature extraction. There's no learning there. And then the learning happens only in the weights of the classifier. Now, the question is, instead of using these handcrafted features, so when I was using this edge detector, I had actually handcrafted that kernel, right? I had said that the kernel has to be this -8 at the center and 1 everywhere around it, right? So I had handcrafted this because I knew that if I use this filter, I'll get the edge detectors. And I knew that if I detect edges, then between these 4 classes, it should be easier for me to classify them because I only care about the outline. So I had handcrafted these kernels. Now the question is, instead of handcrafting these kernels, can I learn these kernels also? So these are actually weights. I have set the weight of the pixel at 1,1 to be 1, at 1,2 to be 1, and so on, right? These are some weights which I have set manually. Instead of setting these weights manually, can I learn these weights? Okay, that's the question which I am asking, okay? And that's the difference between those static handcrafted features and what you do in something known as a convolutional neural network, where along with the weights of the classifier, you're also trying to learn the weights of the filter. Is that fine? So instead of using these handcrafted weights, you learn some other weights for the filter. Now, in all the easy examples that we considered, which was blurring or sharpening or edge detection, when I gave you the filter, even before seeing the output, you can exactly tell me what the output is going to look like. Most of you are able to answer that this will sharpen, this will blur, this will detect edges, right? But here I might get some random filter values, which as humans, you and I may not be able to interpret it. So here this is actually a real filter computed from one of the convolutional neural networks. And you cannot make any sense of these values, right? These values are some very small values, and you don't know. If I ask you if I apply this filter to that image, you won't be able to tell me that that's the output that you're going to. But that doesn't matter, because it's not whether you can interpret it or not. What I care about is, I want to learn these weights in such a way that my classifier job improves, right? My classifier does a better job of classifying between these 4 classes. So instead of handcrafting these weights, I want the classifier to learn these weights on its own. How to do it, it's not clear, right? We'll have to see how to do that. But that's where I'm going. From these static kernels, I want to go to learned kernels. Is that okay? Does that intuition make sense? Now I'm going to take this idea a bit ahead, a bit further. Why just settle for one set of weights? Why not learn multiple kernels? Each of these kernels will learn multiple things, right? So one would learn blurring, one would learn sharpening, one would learn edge detection, and one would learn things which you can't even interpret, right? You just learn some transformation of the image. So I have these multiple transformations. So on the original 900 or 30 cross 30 image, I've come up with multiple images which are abstract representations of this original image. And now I could feed all of this to the classifier and let the classifier decide what is important for it. Does that make sense? So from an original input of size 30 cross 30, I've constructed multiple inputs using this convolution operation, and I'm feeding it to the classifier. Now the classifier can decide whether edge detector is more important, or blurring is more important, or sharpening is more important. Because earlier that decision was with me. I looked at the problem, and I decided that edge detector makes more sense here. But now I'm saying I learn multiple filters and let the classifier decide what is important. And why stop here? What else can I do? So think of this in terms of what we did in a feed-forward neural network. So the original image is actually your input. What is this? This is the first hidden layer. Right? From the input, I have computed some hidden representation, and that hidden representation I'm going to feed it to the classifier. Does that make sense? Does that analogy make sense? Everyone fine with this? But in the feed-forward neural network, how many hidden layers did I have? As many as I wanted. What is the corresponding analogy here? I can take this output, apply further convolutions to it, and get one more representation. So I can do the following. I took the original input, applied a bunch of convolutions to that, got some intermediate hidden representation. I took this as my input now, applied some more convolutions to it, and got another hidden representation. And this hidden representation is what I'm going to feed it to the classifier. And all of these weights, I want to learn along with the weights of the classifier. Does that make sense? Okay? So do you get the full connection between feed-forward neural networks and convolutional neural networks and handcrafted and so on? I'll try to complete the story for you, right? So originally what we did is, we took the raw image as it is, and we fed it to a classifier. Then we realized that, no, this raw image may not be good. Maybe handcraft some features, come up with a better representation for this image, and then feed that to the classifier, and hopefully the classifier would be able to do better. And until 2012, people were coming with better and better ways of coming up with this representation for the input. And one of those ways was sift features and hog features, which is some transformation applied to the image. Okay? Not a transformation, but something computed from the image. Fine? So now you take these handcrafted features and feed it to the image. Now what we are trying to do with deep learning is that instead of doing this handcrafted computation of features, we are going to learn these transformations also. So we are going to learn what kernels to apply, and not just one kernel, but multiple kernels. So the first layer that you see there is one set of kernels applied to the original input. Then we decided why to stop at one layer. So this is the first hidden representation that you have computed for the image. Why feed that to the output layer? We could have multiple hidden representations. So take this hidden representation, apply some more convolutions to it, compute a new hidden representation, and feed that to the output layer, right? And you could do it for as many layers as your compute plus GPU and so on supports, right? And as many as are important for the problem that you're trying to solve, okay? So now, starting from the convolution operation and connecting it to feed-forward neural networks, what we have is a convolution neural network, which has this original input, applies a series of convolutions to it, comes up with a final hidden representation, and then feeds that to the output layer. Does everyone get this? Is that fine? Okay. So I get this idea that you take the original input, and you want to learn some kernels or filters by just treating them as parameters of the model, and you learn these parameters along with the parameters of the classification model. But this is exactly what I was doing in a feed-forward neural network, right? So the feed-forward network would have been the flattened Taj Mahal image with 900 pixels, compute one hidden representation of size 100, another hidden representation of size 100, and then feed it to an output layer of size 4. That would have been the feed-forward neural network for this problem. So how is this any different from that? Again, I'm doing the same thing. I'm taking the input, applying some transformation on that, taking the transform input, applying some other transformations to that, and then feeding it to the output. So how is this different from a normal feed-forward neural network? Same. There again, you are learning the weights. The weights decide what your hidden representation is going to be. You never learn the hidden representation. What you learn is the weight, right? So here also you're learning weights, there also you are learning weights. It's just that here I'm calling the weights as filters, and there I was referring to them as weights. So is that the only difference?
No, sir. Here the activation function that we are using is kernelization.
Good. So let's try to see that difference, right? So now I'll just shift to something more manageable, which is digit classification. So you're given the image of a digit, and you want to classify it into one of 10 classes. Is that fine? Okay. So this is what you would do in a feed-forward neural network. This is the 4x4 image, so I have 16 pixels. So my input is of size 16. Then I'll have outputs of size 10, because I want to predict one of 10 classes, right? So input is of size 16, outputs of size 10, and in between I would have multiple hidden layers, which will feed to the output, okay? And now focus on this one pixel here in the hidden layer, the first pixel in the first hidden layer. How many inputs does it depend on? All the 16, right? So this is actually a very densely connected neural network where every input in the next layer depends on every output in the next layer depends on every input in the previous layer. Is this the situation in a convolutional neural network? Every pixel depends on only the neighborhood. So you see that? Okay. So let's try to understand that. So this is what a feed-forward neural network would look like for this problem. There are many dense connections here, and I told you what these connections are. Now let's look at the convolution way of doing this. So I have this 4x4 input, and I've taken filters of size 2x2. So if I place a 2x2 filter on pixels 1, 2, 5, and 6, I'll get one output. Is that fine? If I place it on pixels 2, 3, 6, and 7, I'll get the other output. Is that fine? Okay, and I can continue in this way. So let's look at the first pixel that we are going to compute, right? So that depends on pixels 1, 2, 5, and 6. Because I'm going to place the kernel over there and only take a weighted average of these 4 pixels, and that will give me one value. As opposed to in the feed-forward neural network, what would this depend on? All the 16 inputs. Do you see the difference? Okay. The convolution operation only depends on a few pixels. What about the next guy? Assume that I've taken a stride of 2 here, right? So it will depend only on pixels 3, 4, 7, and 8. And in this way, you can continue. So all the outputs in the intermediate layer depend only on a few inputs in the input layer. Does that make sense? Okay. So the connections here are much sparser than what they were in the case of a feed-forward neural network. I can actually represent it like a feed-forward neural network. You can just think of it that most of the edges are zeros. You can think that all the edges are present, but most of them have 0 weights. That's one way of looking at it. Does that make sense? So this is a much more sparser connection as compared to a feed-forward neural network. You have a doubt? Yeah. So That's a good question, which I'll not get to in this part, but I'll try to answer that. So that's a 2 cross 2 kernel, right? So now that is trying to capture that 2 cross 2 pattern. So each of these kernels is trying to capture a pattern. Now you could imagine that as training progresses, okay, the rest of you can just ignore this question for now. As you can imagine, as the training progresses, if it starts seeing this curve, right, then this pixel h11 is going to take on a high value. So if you stride this kernel anywhere, and anywhere if you see this curve, or let's take the example of a 3, which has this cusp at the center, right? So you want to capture that cusp, because that's an indicator of either a 3 or a 8 or maybe some other digit also, but definitely not an indicator of 1 or 4 or something like that, right? So whenever you place the filter there, you would want it to produce an high output. That's what your training should do. So this filters, the multiple filters that you will learn, that's why you need to learn multiple filters. Each of these will try to learn a different pattern in your input. Some of them will try to learn these edges. Now if you want to detect a 1 or a 7, you need to learn these vertical lines or a slanted line and so on, right? So those are the patterns which this filter should try to capture. So now I can say that the input figure is a 2 if the filter which captures the bottom horizontal line fires, if the pixel which captures this curve fires, and if the pixel which captures this curve fires, and the pixel which captures this diagonal fires. No, only the pattern, right? It has to be position invariant, because even if I shift the 2 to a different position, you should still be able to detect it as a 2. Is that fine? Does everyone get this, roughly? Okay, fine.
So this means that each of these filters have to get a particular part of the whole.
Yes. That's by design, right? Because you're only localizing it. You're never looking at the full input. You're saying that, so you can think of identifying a dog, for example, as identifying ears, tail, eyes, a particular type of nose, and so on, right? So you don't need to look at the whole image. You just need to look at these patterns. And all these patterns are localized. An ear would probably be a 15 cross 15 patch in the image or something like that, right? That's why you have these smaller connections. You don't need to look at the full dense connections, okay? In a few minutes, I'm going to contradict myself, but I'll do it well, okay? So this convolutional neural network has much more sparser connections as compared to a feed-forward neural network. But are sparse connections always good? And that's where probably she was heading, right? That you're not looking at the whole image. Then how do I know that the whole image is 2? All I am seeing that there's a slight curve here, but that does not tell me. It could have been a 3 also, it could have been a 9 also. So are sparse connections always good? Or are they, so what does a sparse connection tell you? That the pixel 1 at the top is not interacting with the last pixel at the bottom. That's what a sparse connection basically tells you, right? But is that really the case? Think of multiple layers. So let's see what happens when you have multiple layers. So look at the input which was x1 to x5. Now look at the 3 gray pixels in the first hidden layer. Okay? Now in the first hidden layer, x1 does not interact with x5, because each of the outputs depends only on 3 inputs, right? So now using x1 to x5, you have computed h1 to h5. Now focus on h2, h3, h4. Now in the next layer, these guys are going to interact with each other and produce g3. Now g3 depends on h2, h3, h4, but h2 depends on x1, x2, x3, h3 depends on x2, x3, x4, and h4 depends on x3, x4, x5. So in turn, now g3 depends on all the inputs. Does that make sense? Right? So transitively, now you'll start seeing stronger connections. But at each level, you have sparser connections. So by doing sparse connections, you're not necessarily losing out on the bigger picture. So what the G3 should try to do is, it should try to fire when you see a ear, when you see a nose, and when you see an eyes. So then probably it's some animal or human or something like that, right? As opposed to a car or a bus or something like that, right? So these higher level interactions between the distant components of the images will get captured as you go deeper and deeper into the network. Yeah, number of layers, yes. So there are certain standard architectures which are there on the slides. You can take a look at them. So you have typically a deep convolution neural network. Because of this sparse connectivity and something known as parameter sharing, which I'll do next, you can actually have many, many layers, because even though you have many, many layers, you have very few weights in your network, right? So typically a deep convolutional neural network would have 8 to 10 layers, but the current state-of-the-art networks have up to 50 to 150 layers also, right? So they are as deep as that. Okay? Fine. So the other characteristic of CNNs is weight sharing. Now consider, and that's the part where I contradicted myself, right? So it was sparse, but not really sparse if you look at the bigger picture, okay? Now consider the following network. You have these two kernels, right? The orange kernel and the pink kernel. So the orange kernel is actually operating on the first 4 pixels, and the pink kernel is the one which operated on the last 4 pixels. And I've depicted them as orange and pink because I want you to understand the weights are going to be different, right? So the orange kernel will have 4 weights, and the pink kernel will have 4 different weights. Now, do we really need to have 2 different sets of weights? No. So now suppose you want to detect a 2. And suppose this is your image size. Someone has written a 2 here. Someone has written it at the center. Someone has written it at the bottom. Someone here, someone there. Right? Now you're applying this kernel to all the pixels. Now, what I'm saying is that when I place the kernel here, I'm going to use a different set of weights. When I place the kernel here, I'm going to use a different set of weights. Is that the right thing to do? What does the kernel have to do? It has to capture patterns, irrespective of where they appear in the image. So now imagine this. In fact, you should be able to answer this based on the exercises that we did. When we did the blur detector, what did we do? We applied the same kernel throughout the image because we wanted the blur effect throughout the image. When we applied the edge detector, we used the same edge detector throughout the image, irrespective of whether we are placing it near the dome or near the pillars or near the lawn. Right? So one filter has to be applied throughout the image. Right? So these 4 weights that you see, they need not be different weights, they can be the same weight. So one same filter applied throughout the image. So it's the same filter applied to pixels 1, 2, 5, 6 will give you one output. The same pixel or the same filter applied to 3, 4, 7, 8 will give you a different output. Right? But the filter has to be the same. But now this is very restrictive, right? I am saying that you just have 4 weights in this network. But that seems to be very less. How do I get away with this? So this is known as weight sharing. You're sharing the weights because you're using the same kernel throughout the image. Right? But now I'm left with only 4 weights. How do I get by that situation? I can always use more kernels. Right? So I have one kernel which is trying to detect one pattern. I can have several other kernels which are trying to different patterns. So each of these kernels will have different weights. But when I apply it to any location in the image, it has to be the same kernel. Right? So I'll apply the pink kernel throughout the image. I'll apply the orange kernel throughout the image. And I'll apply the green kernel throughout the image. And each of these will try to capture a different pattern. And each of this will give me a different pixel value. Right? So these are the 2 characteristics of a convolutional neural network as compared to a feed-forward neural network. It has dense or sparse connections. Sparse. And the second thing is, unlike feed-forward neural network where all the weights were different, here all the weights are shared. The same kernel is applied throughout the filter, and you have multiple such kernels. Okay? So that sums up the introduction to convolutional neural network and how they are related to feed-forward neural networks. And the 2 main ideas was weight sharing and sparse connectivity. Right? Now let me ask you this question. If you have an algorithm for training a feed-forward neural network, can you use the same algorithm for training a convolutional neural network? Imagine a very deep convolutional neural network. Now, at the high level, at least this idea should be clear to all of you, that you can use gradient descent for learning the weights of the network. Okay? All you need to do is compute the partial derivatives. In a feed-forward neural network, we are computing the partial derivatives by looking at the path from the output to the input. Is that fine? In a convolutional neural network, can you do the same thing? A feed-forward neural network was very dense, so there were multiple paths from the output to the input. Now, can you do the same thing in a convolutional neural network? Yes. All you have to do is assume that all these paths which do not exist actually are connected with weights which are 0, and those weights are never going to change throughout the training. So you can think of a convolutional neural network as a feed-forward neural network with many 0 weights which you're not going to learn at all. Does that make sense? Is that fine? So the same algorithm that you use for training a feed-forward neural network, you can adapt it for training a convolutional neural network also. It's just that you have much fewer weights, and that's why the paths that you need to compute the chain rule over are going to be much sparser. That's all. Okay? So I'll end with that, and we'll have some tutorial sessions in the second half of the course. Okay? Okay, thank you.